I have talked of some of the ceramic synthesis methods by which we can generate ceramic powders. There are lots more and I shall cover some of them. But today I want to emphasize on a method which is the one that is possibly can be developed well into the future, because today the demand is one of green materials, means materials which impose as little thermal load or environmental load, that is gases, that evolution of gases should be minimized, use of energy which again leads to evolution of gases should be minimized, and such one process is hydrothermal. I had stated long back that today we are trying to mimic nature. There are plenty of hydrothermal vents in the world where reactions happen under the occurrence of high temperatures and pressure. Now, why are we going to do that? I will just illustrate it with a slide, and I shall emphasize on this one for a short time. On the x axis, I have a temperature scale, and on the y axis, I have a pressure scale. This is somewhere where the atmospheric pressure is. If we use pressures above this, we will be increasing environmental load because it will require heating or adding gases which has been synthesized or fractionated from the air by using electrical energy. This is 0 degree centigrade, somewhere room temperature is here. So, if we adopt temperatures above this, again environmental load will increase. Our goal or the drive today is to have some synthesis process which works around this zone. I will elaborate on this, but let me say hydrothermal processing occurs roughly in this zone. This is the area of hydrothermal processing, the topic of my today's lecture. But before I go on, while I am on the subject, I would like to talk of where are the others. For example, ceramics are made say by hot wall reactions, that is, we have a vacuum chamber which is evacuated and gases, reactive gases are pushed in through this and the sides are heated. Let me take for example, silane SiH4 and through this oxygen. SiH4 plus oxygen give you silicon dioxide, and this is the material which is used for making optical fibers, because here by controlling the purity of silane and controlling the purity of oxygen, we can get ultra pure silicon dioxide. This is a common method. Where does it stand on this particular scale of environmental load? Obviously, silane, everything comes over somewhere over here. This is where the hot wall reactors are, or it may be spreading to lot more. In addition to hot wall reactions, ceramics thin films, ceramics, especially thin films, which I shall talk of later, composites. These are made by thin film processing, thin film technique, and this is done in vacuum. This can include evaporation, this can include sputtering, this can include plasma process. These are three broad ranges. Evaporation can be done under different conditions, sputtering can be done under different conditions, and so can plasma. Where do they stand? They really load the system, especially the plasma. I had earlier talked of solid state reactions. That is, I took solid state reactions. I took, for example, barium nitrate plus titanium dioxide, reacted them to give you barium titanate. This is a solid state reaction. On this diagram, where does a solid state reaction stand? It stands somewhere over here. I have also talked of sol gel processing in brief, and I shall talk of it more. Sol gel processing comes somewhere over here. Hence, as it appears, hydrothermal method of processing portends to be a good method of generating green ceramics, at least in the fine powder form, and I shall talk of it. But before I do, I would draw your attention to a particular slide. What I did was I googled hydrothermal ceramics, or rather let me go back, so that because the lettering is very small, I googled and this page comes up. I would click on this link, Clean Materials Technology Group. Now, this is not an open source, so I cannot go deep into it. I am just indicating the URL, which is over here, and you look at this particular page. This page gives you a reasonably good idea of what hydrothermal ceramics synthesis process is. Another good one which you should be looking at is, if you click on this link, hydrothermal synthesis, which is, let it come, it has got a couple of videos, and Let the video come, it's taking its time. Now, it did not come. So, let me try a rescan. While this video comes, why I want you to look at it, in this particular lecture, which was focusing on synthesis of lithium batteries. Lithium is a very high energy density material, and it looks as if that is a good source of way of saving energy. I don't get this page. No, I don't get this page. I'll come back to it later. Let it be there. So, here what we have is this particular process, hydrothermal process, which is so called environmentally friendly. Now, there are a couple of good papers which are available, or books. I would recommend them for you to read. One is the basic old one, the first one is Hydrothermal Synthesis of Fine Oxide Powders, and it is authored by the two greats Rustom Roy and Soumya Saka. Rustom Roy developed this method back in 1950s, and Soumya carried on his work. The second one, I would really ask you to look up this particular paper, which is a very, very good reference paper, is by Kumar Neni and Rustom Roy. This particular paper is an excellent one because it takes off where Rustom Roy let off, or where the problems of conventional hydrothermal ceramics could be addressed. A very late paper is this particular one. This is a small paper, but still it addresses or gives you many issues which hydrothermal ceramics is concerned about. Back in 1950s, what Rustom Roy and his group dwelt on was the three-phase diagram of water. Okay. This was the triple point. However, what happened later was that it was realized that the water could be taken to a supercritical point. This is the supercritical point. This corresponds for water to 647 degree Kelvin and 22 megapascal pressure. In this particular zone, above this zone, it was all a super critical liquid. it was realized that over here in this supercritical liquid zone, what happens is the liquid has the property of both the liquid and the gas, and as a result above the supercritical zone solubility decreases, reactions which were hitherto unknown under normal temperatures and pressures are entirely changed. This was first realized by a gentleman called this particular person, Bridgman. He was the person who back in 1920s really realized that above certain temperatures and pressures you could really change the property, whether it is solubility, precipitation, reactions of anything. I would ask you to really look up this particular link, the Bridgman seal, because it's not a public document and hence I cannot go into it. But if you just wiki in Google Images Bridgman seal history, as I did, you will find out the basics behind this chemistry in supercritical state. Essentially, what happens is, let us say I have got a metal ion in solution and I am below the subcritical temperature, the supercritical temperature. As I said, supercritical temperature is 647 K, 22 megapascals. I got metal ions in solution. Let's say this is somewhere around, for just say 500 K, 10 megapascal, let us presume it. What would happen? The metal ions would nucleate, there would be only a few nuclei, these nuclei would grow to give you large crystals. But if we are above supercritical temperature and pressure, which is greater than 647 K and greater than 22 megapascal. What would happen over here is there would be huge number of nuclei which would be stable now at these elevated temperatures and pressures. There would be huge number of nuclei contrary to over here, and as a result the presence of this huge number of nuclei would prevent the nucleation and growth which has occurred over here. So, because each nuclei would impinge on another nuclei, each of the nuclei is stable. So, here I would get very fine particles, and as a result I would get very fine grained ceramics. Whereas here, because the number of nuclei are small, the crystals would grow on this small number of nuclei, leading to very large crystals. So, hydrothermal method combines two aspects. If I can go above the supercritical temperature and pressure, I can generate very ultrafine particles and also something more. Let us take the case of example of a very simple example. Let me take aluminum nitrate. In water and add urea. Urea is CONH2 twice. I heat it, let me say at 200 degrees centigrade under say 5 megapascal pressure. First, the urea would dissociate to give you in presence of water, give you NH4OH. Now, this is a very slow process. The urea would hydrolyze in water to give you NH4OH. This would react with aluminum nitrate to give you aluminum hydroxide. This is a standard thing that would happen under these conditions of temperature and pressure. And the aluminum hydroxide over here, as I said, because I am below the supercritical temperature and pressure, it would form large grains. And as a result, if I want to get alumina from here, if I require alumina or Al2O3, this would require calcination or high temperature heating. This would obviously increase the environmental load. So, our goal is really how to synthesize these ultrafine oxide powders. That is, here I want alumina if I want. If I want zirconia, I will settle for zirconia, but not aluminum hydroxide. I do not want zirconium hydroxide. I want these products like these, the oxides directly. The way this hydrothermal method works is, what is done, let us take, imagine you have seen the pressure cookers at your home. What is done, the pressure cooker is taken, the bottom is filled with water, and then in a container you place whatever you require to cook, close the lid and heat it. Under the normal weight of the pressure cooker valve, the pressure cooker heats to up to 121 degrees centigrade, because it is almost 15 atmospheres, that is the weight of the lid. But here in hydrothermal synthesis, I am talking of much higher temperatures. In fact, ideally I am talking of 647 degree Kelvin, and pressures much larger than 22 megapascals. a conventional pressure cooker cannot do it. So, what is done is we have a specially constructed steel vessel. This will be a specially constructed steel vessel with a Teflon lining. This is steel, this is Teflon. The reason why Teflon was put in is water is very corrosive by itself. Water would react with steel, producing an oxide layer by itself at these temperatures. So, we required a lining which would be resistant to attack. So, a Teflon vessel was chosen because of its chemical stability, because of its high softening point, and that it is nothing sticks to it. I am showing you on the screen this construction of such a vessel, but because of IPR limitations I cannot expand. All I did was I went to Google Images and then I typed out hydrothermal synthesis reactor. If you look on the screen, it shows different types of hydrothermal synthesis reactors. The white parts are the Teflon, while the gray parts are the stainless steel cylinders. Unfortunately, I cannot go beyond this because of intellectual property restrictions. You will have to explore these yourselves and understand what the reactors are. The reactor top is then sealed off. The liquid is poured in. Here we have got the liquid plus the metal iron reactants plus at times we use precipitating agents like I had used urea, and at times we do use surfactants. We do use surfactants. The whole thing is sealed, screwed in, gas is pumped in to elevate the pressure to the desired level, and the whole thing is then heated to the desired temperature. With Teflon has a limitation. Teflon can go up to max 240 degrees centigrade, which means 513 Kelvin. This has been a severe limitation of hydrothermal synthesis. That is, because we are using steel, steel will corrode. So, to protect the steel, we put in a Teflon lining. The Teflon lining softens. So, with all those conventional reactors that I showed you, the maximum temperature they can go up to is 510 K. And there our problem is that, if I come back to this slide, is because it is a subcritical temperature range, we are stuck with hydroxides. But before I go on, I would like to introduce you to the idea as to how at this pressure, say 513 K, let us assume 20 megapascals, how is this sealed? Because this is a tribute to Bridgman himself. It will take me only a few minutes, but this is a fantastic innovation which led to allowing hydrothermal reactions to occur. This whole picture is the seal part. This is liquid. Like on the pressure cooker you have a vent hole. So, this is the vent hole. To hold the pressure, what they have done is, here they have got a steel plug which is marked as A, which can move, and this is the piston. So, you have got something like a steel plug moving in a piston and causing the seal. So, here how do we do it? This steel plug moves on the piston. Here they have got a soft rubber. As it presses in, this soft rubber will expand, causing this level huge pressure on this area. As this soft rubber expands, there is a soft steel over here. This steel will bulge, and as a result the seal will improve. So, even though I have got very high pressures over here, let us say 50 MPa, the gas will not go out, because first the rubber will seal it, next this soft steel seal is there, and then the hard steel seal is there. So, the gas vapors which are generated in this zone cannot escape from here. So, the simple weighted seal that you see in your homemade pressure cooker is replaced by this complex Bridgman seal, because we are operating at much higher pressures than what we use for pressure cookers. But before I go on to some hydrothermal reactions, let me say our limitation is still that because we do not have strong enough lining, that is a steel, and the Teflon softens at 513 K, it is very difficult for us to go anywhere near the supercritical temperature using a Teflon lining. What people have done, like say Kumar Neni, he used an innovative process. What he did was, again I am drawing the steel shell, the Teflon lining, the top is sealed, this is heated, gas pressure is imposed. The innovation that Kumar Neni did was, he put in a probe which would irradiate the solution with microwaves. You have microwave ovens at your home. You use it for cooking. The very fact that this is now being irradiated with microwaves at the elevated temperature, at the elevated pressure, this simple addition of a microwave allows, for example, the aluminum nitrate in presence of water to form aluminum hydroxide, which does not allow required volume of aluminum oxide. It simply goes on to precipitate aluminum oxide. If I am dealing with, say, I require stabilized zirconia powders, we can take zirconium tetrachloride solution, yttrium tetrachloride solution, urea, mix them and microwave assisted hydrothermal. We get straight away we get yttria stabilized zirconium oxide powders. We simply get yttria stabilized zirconium oxide powders. The reference that I had told you of Kumar Neni himself in the particular paper I had shown, this particular paper over here, microwave hydrothermal synthesis of ceramic powders, this shows you the different types of innovations that are being made for hydrothermal synthesis of ceramics. Today, we not only have fine powders of like say you take anything alumina or anything, but also we have complex systems like barium titanate, yttria stabilized zirconia, this paper goes on to talk of manganese oxide single crystals. The hydrothermal method allows you a lot of access, lot of avenues or ways to prepare these ceramics in a very, very benign fashion. The other area where hydrothermal synthesis is playing a very, very big role is recovery from natural materials. For example, today titanium dioxide, this is a very important antibacterial material. It is used in paints, the white paints that you see in the market which says fungus won't grow are based on titanium dioxide. I told you that. Aseptic hospitals, white wall tiles, white float tiles use titanium dioxide extensively. Even in hospitals, to prevent secondary infection, whatever you see in the bathroom toilet is white and is germicidal. They require titanium dioxide. The requirement for titanium dioxide is growing very, very hugely, and the world is running out of it. So, long back in I think 1960s, the technology was developed, but is being commercialized only today. And the source was ilmenite, a natural rock with a composition of FeTiO3. This occurs in huge areas, and we did not have a method of recovering titanium dioxide. Here, hydrothermal reaction comes to the rescue. If ilmenite, this material is water plus 10 molar sodium hydroxide or potassium hydroxide at 500 degrees centigrade and 20 atmosphere pressure, this would give you Fe3O4 plus TiO2 under microwave irradiation. This is an example of microwave assisted hydrothermal reaction, and this method is being increasingly developed for synthesizing powders from sources which were so far merely we did not know how to handle it. But this method also allows us to have powders formed directly from solution. Again, here we can control particle size also, particle shape, chemical composition. All of these can be controlled because these powders are being generated from the solution itself. I had shown you that by controlling the nucleation rate of nucleation, we can have very large number of nuclei, and all of these can be controlled. And if we have ultrafine powders, sintering will be faster. In all these cases, the other advantage that we have is one more important thing. The powders obtained are not, this is the most important thing, are not agglomerated. So, no milling required. That means that I am not going to introduce contamination while trying to deagglomerate the powders. This is a very, very powerful tool to make unagglomerated powders. Particle sizes can range from 50 nanometers to much larger. I would now show you a video from YouTube which shows today how these powders are synthesized. You can search this up. Apparently, they are generating powders in test tubes, but there are tens of thousands of such test tubes which are being processed, and as a result what happens is the product yield is in tonnage. You see what, just look at what is being written. I didn't talk. All of this process is non-contact because it's done in ultra clean rooms, because even a small amount of dust particle would cause heterogeneous nucleation. Look at the color of the suspension, it is black. This will be ultracentrifuged at the next step. It is picked up remotely, placed into the ultracentrifuge, and this is not one tube, this is a demo video. So, they are showing you only one tube only. In reality, at a time 100 tubes are centrifuged. Centrifugation over. It is a just clean white powder. Now, the question is, why did it look black earlier and white now? There is quantum size effect. It was so fine that there was quantum confinement and the color was different. So, here the material has been centrifuged and the liquid will have to be removed, so that unreacted reactants can be removed. Here the liquid is being pulled up from the centrifuge sample. The sensor checks if the liquid level is all right. The waste liquid is thrown out and more cleaning solution is added. More cleaning solution is added. You will see at the next step, this is ultrasonicated. This is ultrasonic probe which goes in. It mixes up the liquid with the solid which was ultracentrifuged, so that any unreacted reactant again comes to the liquid phase. This will be ultracentrifuged again, the liquid removed. Here they are topping it up. And as you can see, the samples are recentrifuged. The cycles 8 to 12 are repeated several times until they are sure that the unreacted reactants are not there. At the final stage, they have got a clean slurry which is returned to the rack for further processing. Now, let's see what they do with the slurry in this particular video. They will print quantum dots. These are the quantum dots, nanoscale dots, which they have printed. Now, the thing is, if you feel that these are done only in test tubes, sorry, this is a tonnage operation. There are thousands of carousels which are spinning parallelly. The reason I showed you the video was to emphasize that this is a commercial thing. If you look at the number of publications, patents, products which are coming out, China is a leading country with over 40% of its products being synthesized by hydrothermal route. Japan is next. One of the reasons why Chinese can supply materials to us at a much cheaper rate, frequently we find that, let me take the example of barium titanate. We want to prepare ultra pure barium titanate. The cost of the finished product of Chinese is lesser than what is the cost of just the synthesized product. The reason is the Chinese extensively resort to hydrothermal and other processing methods in parallel scale, reducing the cost, while we are using single unit operations. I would urge you to read the papers, the reference papers I had shown you, especially the classic one by Rustom Roy, Komar Neni, and look at how innovative they were in developing the hydrothermal method, so that they could modify the situations so that they work near the supercritical temperature and pressures and get the nano sized or the ultra fine sized oxides directly. I think I will stop over here, and the next lecture I shall start with sol gel processing of ceramics.